Good morning, everyone. Good afternoon as well for anybody from Far East or the other side of the world. And thank you for the team, Valerie, Lowen, and Maria, for inviting me to speak today. It is truly a privilege to discuss how building airtightness is used to evaluate the energy performance of homes in the UK. I'm sure there are certainly a lot of people with deeper expertise on this topic. I'm honored to share my perspective and contribute to the conversation. I can't claim absolute perfection in every detail. However, I do hope this talk will spark some meaningful discussions and encourage knowledge sharing among all of us. Sorry, jumped a little bit. The talk will cover three main aspects: energy impact of building airtightness, UK adaptation, and space for improvement. Under the UK adaptation, I will talk a little bit about the inclusion of poles in sub 10.2. So airtightness plays a crucial role in building performance, particularly in determining the energy required for heating and cooling. So measuring airtightness provides a essential starting point for evaluating filtration heat loss. Filtration can account for up to 1/3 of the building's heating load, with some studies reporting even higher figures. So once infiltration is known, it is straightforward to calculate its heat loss. Since direct infiltration measurements are often intrusive, expensive, and time-consuming to implement, so airtightness is typically measured instead. But how can we quantify infiltration heat loss based on a building's airtightness? So leakage infiltration correlations are commonly used to estimate infiltration rates, though these correlations remain complex due to the many variables involved. As we know, infiltration refers to the airflow through the building envelope driven by environmental conditions, while fundamentally determined by a building's airtightness. It is also influenced by a range of factors, including building characteristics, environmental conditions, and the surrounding factors. So accurately quantifying the individual impact of these factors remains a significant challenge. So this topic has been studied and debated in the field for many years, like over 40 years, so leading to many valuable developments, most of which, however, still rely on certain level of assumptions being made. So as climate changes, the increasing unpredictability of weather patterns adds another layer of complexity. Although the relationship between the leakage and infiltration is complex, a positive proportional correlation between the two still exists under specific environment and surrounding conditions. So I produced this graph based on a home with a volume of 200 meters cubed. So as buildings become more airtight, infiltration heat loss decreases. So this graph provides a rough depiction of the minimum airtightness requirements set in building regulations across Europe and North America. Over time, building regulations have increasingly emphasized airtightness driven by stricter energy efficiency standards. However, as buildings approach high levels of airtightness, its energy impact tends to diminish. Well, in the UK, the minimum regulatory requirement still permits relatively leaky buildings, suggesting that airtightness will continue to have a significant impact on energy efficiency for decades to come. Therefore, the leakage infiltration correlation remains highly relevant in the UK. Interestingly, Ireland is several years ahead of the UK in its progress towards net zero buildings. It is fascinating to observe how Ireland's regulations have evolved and how the average air permeability of dwellings has improved at the same time, given the fact both countries had the same starting point before. Please don't dislike me for saying that, my dear British friends. So once insulation levels in a building are improved and thermal bridges are addressed, ventilation heat loss become a major factor. And this figure taken from a good practice guide to airtightness by Passive House Trust highlights how infiltration heat loss can make up a significant portion of overall heat losses in a low energy buildings if airtightness isn't carefully considered during design and construction. This makes me wonder, is highly airtight and mechanically ventilated home the future? So the graph, the photo on the left shows what might look like in the future in the sci-fi. But the photo in the middle, it kind of shows what it actually looked like last year in New York. So this the famous skyline, but it's heavily polluted by the wildfire happening in Canada. So as climate change intensifies, processing outdoor air becomes essential for airtight homes to ensure safe and healthy indoor environments. So while airtight mechanical ventilated homes offer energy efficiency and controlled air quality, the reliance on ventilation systems raises concerns about vulnerability during power outages or system failures. So to address these concerns, the future trend may involve a balanced approach integrating airtight designs, mechanical ventilation systems with fail-safe mechanisms, natural ventilation options, and robust maintenance protocols. So such hybrid solutions would aim to combine energy efficiency and resilience while addressing potential vulnerability. In the UK, current building regulations are expected to adopt highly stringent airtightness requirements in the coming decades, so relatively leaky homes are likely to remain the norm for the foreseeable future. So this regulatory approach contrasts with trends in some other countries moving towards tighter standards to reduce energy consumption and emissions. So given this context, understanding the energy impact of building airtightness in the UK remains important. While leaky homes allow for natural ventilations, they also contribute to significant energy losses, undermining efforts to improve energy efficiency and sustainability. So by better quantifying and addressing the relationship between the airtightness and energy performance, the UK can identify practical and cost-effective solutions to optimize building design while aligning with its broader environmental goals. So that said, it's not all pessimistic. In the past 5 to 10 years, new built homes in the UK have been built to 4 to 5 air change power at 50 Pascal. The mean air change power at 50 Pascal of existing homes in the UK is in the range of 8 to 10. Models have been developed over the last few decades to mathematically represent the leakage infiltration correlation. Most of them treat the buildings as a single zone. Some are simplified. For instance, LBO and aim to rely on superposition techniques that simplify the calculation for air infiltration. Models are similar to each other with a proven accuracy. So within the UK, SAP, short for Standard Assessment Procedure, is the UK government's current go-to system for figuring out how energy efficient a home is and how much CO2 it produces. It looks at things like construction materials, insulation, heating, air leakage, ventilation characteristics, and also whether the home uses renewable energy to come up with a rating. So how is infiltration estimated in SAP? So it's currently done in 2 different scenarios. So when the measurement is not taken, so when I say measurement, it means airtightness. So infiltration is estimated using empirical values assigned to different building elements and functions. So here are at least 5 of them. So it depends on the number of stories in the dwellings, also depends on the structural of the building, and also whether the ground floor construction is a certain type, and whether the building has a draft lobby, also on the percentage of windows and doors draft proof. Under the new future home standards, this approach will likely become obsolete since airtightness testing will be required for all new dwellings. So when a measurement is taken, the airtightness test given by either blower door or post method can be inputted into SAP for the calculation of infiltration. So with these 2 methods present in the UK regulation, the initial focus has been on so-called ensuring parity, i.e. possible Pascal measurement is extrapolated up to 50 Pascal and then divided by 20. Well, in my kind of personal opinion, it's a little bit of compromise for the latter one. So originally, the divided by 20 rule was proposed in the US, but it was later discarded due to its crudeness. However, it was adopted in the UK with a slight modification. Instead of having the air change power divided by 20, we have air permeability at 50 Pascal divided by 20, mainly because the surface to volume ratio of the UK housing stock is very close to 1. So while I won't delve into the history of this famous empirical ratio, it is important to acknowledge that this simplicity makes it a convenient tool for estimating infiltration. However, due to variation in building materials, sizes, and forms, leakage characteristics can differ significantly across structures. Therefore, applying this kind of ratio directly in the UK context may lead to inaccurate results and should be reconsidered. It's about roughly 4 steps to do this calculation. So once we have an air permeability test is at 50 Pascal, then we use this kind of a divided by 20 ratio. If we have an air permeability at 4 Pascal method, we use this equation here. So you might be wondering what this equation to more details on that. So BIU, stands for Building Research Establishment in the UK, worked with a sample of 100 UK homes running both blow test pressurization and depressurization test alongside post-test. They then validated this data using the N-exponent profile from nearly 293,000 blow tests in the UK. So this formula adjusts for the fact that the M-value changes depending on the leakage level. For example, the M-value tends to be higher when a house is particularly airtight. The second step is to modify the infiltration according to the shelter factor. So it depends on how many size of the building is sheltered. So you can use this equation to calculate the shelter factor. So a side of a building is considered sheltered if there are adjacent buildings or tree height hedges which effectively obstruct the wind on that side of the building. And then the third step is to modify according to the wind. It's based on the monthly wind speed. So basically you can divide the monthly wind speed by 4 to get the wind factor. And the monthly wind speed basically is taken from the weather station, so it varies depending on which part of the UK it is. And then finally, the effective air change rate is then determined based on the ventilation type, for instance, balanced mechanical ventilation with heat recovery and without heat recovery, or the other 2 scenarios. And then we consider the infiltration contributed by chimneys, flues, fans, and plastic stack ventilations. And then finally, we use this equation to calculate the infiltration heat loss. This table just show you, summarize very briefly on, what sort of factors UK staff considered when estimating the infiltration. You can see the temperature difference, the grain class, and the leakage distribution are not really considered against in comparison with LBL model. And to be honest, here I'm not 100% sure about the filter factor here. Maybe someone can tell me later. I didn't find any information in that aspect. Earlier this year, the UK initiated a consultation to explore the use of more refined ratios to better account for the factors influencing infiltration in home energy model. So this move reflects the country's intention to enhance the accuracy of the leakage to infiltration correlation currently used in energy assessment. Is there any space for improvement? I think there is, and can be discussed in 2 different scenarios. So when the leakage infiltration ratio is favored, I think the space for improvement will be, so the divided by rule should be based on the UK data. And also the divided by rule for the post should have its own equivalent value rather than taking up to 50 Pascal. And we also need to have a better understanding of the leakage distribution of UK homes, and also it's a bit of a challenge still in the field. And also perhaps we can consider the temperature difference. From an academic perspective, I think a better leakage infiltration correlation should be considered. The reason I say that is because one of our PhD has had his research done based on 100 UK homes, and reasonably representative in terms of dwelling size, form, and construction. And the results shows leakage infiltration ratio for post, for fan pressurization method. The ratio is at least double of what is currently used, so it's at least 40 instead of 20. And for the post, it's roughly around divided by 9. And another finding we have is the simple leakage infiltration ratio. So compared to that ratio, the LBO model improved the accuracy of predicting infiltration by at least a factor of 2. well, we kind of recognize that this database is relatively small, but it highlights the need for further improvement. So additional studies are essential to deepen our understanding and hopefully address the gaps. Okay, that's my talk today, and thank you for your time and attention.